Hi everyone, and I apologize again about the confusion with the time because I thought the daylight savings was the same for everybody, and my calendar invite ended up in the wrong time. So I apologize again, but thank you that you're here. And yeah, so we're going to talk about quality of research evidence, and we're going to focus on a critical aspect of research literacy, so understanding and evaluating the quality of this research evidence. You have all learned how to design studies, conduct surveys, interpret results, and even synthesize evidence through systematic reviews and meta-analysis, which we discussed about 2 weeks ago. Those are all essential skills for producing and analyzing data. But as researchers and professionals, our work doesn't stop at generating the data. Oh, we also need to ask, can we trust these results? And what makes the study more credible than another study? And of course, also, how do I know that the evidence is strong enough to guide any decisions? And these are the kinds of questions that fall under the umbrella of research quality. In today's session, we will unpack the concepts of validity, reliability, bias, and reproducibility, and look at how researchers use structured tools such as the CASP, JBI, and GRADE to systematically judge evidence strength. By the end of this lecture, you will be able to look at a published paper, whether it's a randomized trial, a qualitative interview study, or a review, and make an informed judgment about its quality and credibility. So let's begin by grounding this topic in why quality actually matters. So research doesn't exist in a vacuum. The studies that we conduct and read influence real-world decisions in clinical care, education, environmental policy, or public health. When evidence is of high quality, those decisions are informed, ethical, and effective. When evidence is poor, then the decisions can lead to wasted resources, patient harm in case of clinical encounters, or even the spread of misinformation. So think, for example, of the retracted studies claiming a link between vaccines and autism. You might have heard of that. That was a scientist in the UK, a doctor actually, who wanted to, well, he actually faked data and found all sorts of data and made it up to put a causal relationship between vaccines and autism. So that he was saying that the measles vaccine is causing autism in children around the age of 6 or 7. And the methodological flaws and lack of reproducibility in those studies caused years of confusion and public mistrust. And actually, this story built a lot of mistrust among vaccines, specifically the measles vaccine. And even after it was debunked or retracted, there is still public mistrust around the topic. And this is why we must emphasize research quality, and not just for academic integrity, but because the ripple effects of bad science can be enormous in the public. And high quality research builds public trust in science and reassures funders, reviewers, or practitioners that conclusions are worth acting on. So before we focus on methods, it's important to appreciate that quality isn't optional because it's the backbone of scientific credibility. When we talk about the quality of research evidence, we are referring to multiple interconnected dimensions. The first one is validity. Validity asks whether the study actually measures or examines what it claims to measure or examine. If a survey is meant to assess health literacy, but its questions only reflect general education level, then the validity will be low. The study might be carefully done, but it is measuring the wrong construct. Second, reliability refers to the consistency of results. If we repeated the study, perhaps with a new sample, would we get similar outcomes? Reliability ensures that results aren't just random fluctuations. Third, we have transparency. A high-quality study makes its methods explicit. You should be able to read the paper and understand exactly how participants were recruited, how data was collected, what instruments were used, and how analysis was conducted. Transparency allows others to critically appraise and replicate this work. So this is something we also spoke about specifically in your original research. So if you're conducting a survey, you must clearly state every step of what you did so that if somebody came back and wanted to do the same study, they were able to replicate it from your methods and the way you described it. And this, of course, goes for systematic reviews as well. If you joined my class 2 weeks ago, we spoke about how systematic reviews, you also write the methods section with all your search terms and everything in that way, so that a person who wants to do the exact same thing can do it just by the way you wrote it up and is able to replicate it. And finally, we have reproducibility, which is a major focus in modern science. So this is exactly what I just heard you mention. It goes together with the transparency, because if other researchers follow the same procedures using similar data, they should reach comparable results to yours. And when studies can't be reproduced, it raises red flags about data handling, analysis, or selective reporting. And together, these four elements, so validity, reliability, transparency, and reproducibility, form the foundation for judging research quality. One practical way to think about research quality is through hierarchy of evidence. This hierarchy reflects the relative strength of different study designs in answering questions about causation and effectiveness. At the top, we find systematic reviews and meta-analyses, which, if you joined my class, we covered 2 weeks ago, and they combine data from multiple studies to provide a synthesized higher level conclusion. They reduce random error by aggregating large amounts of data. So most systematic reviews and meta-analyses will involve at least, let's say, 10 studies, and most of them will be hundreds, and you are looking at the bigger picture. So this is why they are at the highest level, because we're not just looking at one study, we're looking at the combined effects of multiple studies, studying this, essentially the same outcomes. After that, we have randomized controlled trials, often called the gold standard for evaluating interventions, such as a drug or a medical device. So randomization and blinding, in this case, would minimize selection and performance bias, making randomized controlled trials powerful tools for determining causal relationships. So as we know, we often have drug trials comparing the drug to a placebo to, let's say, see if it reduces a certain symptom in an individual. So we are looking for these causal relationships and looking as if the drug is better than the placebo. And the same can also be done with medical devices, or even, to be honest, any intervention you're administering to an individual. Below that, we have cohort and case control studies, which are observational. So they can't establish causation as confidently, but they are essential for studying exposures that can't ethically or practically be randomized. For example, smoking or any environmental toxins. Further, we have cross-sectional studies and descriptive designs, which capture a snapshot in time. They are excellent for estimating prevalence or exploring associations, but not for inferring cause and effect. And this is where, for example, your survey research would align as well. That would be, for example, cross-sectional, because you're capturing a certain responses at a certain time. And finally, we have case reports and expert opinions at the base of this hierarchy. They're useful for identifying new phenomena, generating hypotheses, or illustrating clinical insights, but they offer the weakest empirical support. And keep in mind that hierarchy does not equal importance. Sometimes a qualitative study or a descriptive report is precisely what you would need. But from a quality standpoint, the higher we move up this hierarchy, the more rigorous and controlled the evidence tends to be. Further, we can talk about bias, which I have mentioned also in survey research and in systematic reviews. And it is one of the biggest threats to research quality. In everyday language, bias sounds like a moral failing, sometimes done deliberately or unfairly. But in research, bias simply means a systematic deviation from the truth. And bias can occur at any stage: when participants are selected, when data is measured, during analysis, or even in publication. Often it is unintentional, so a product of human error or structural limitations. For instance, if a study recruits only hospital patients to assess population-level depression rates, the results will be skewed. So it's not malicious, but it's just poor representativeness. So I see that often in my surveys, and it is not intentional for me to, for example, recruit people from one background, but sometimes it happens. I saw in most of my surveys that I had participants from the white Caucasian ethnicity. And unfortunately, that happens. So even when I asked for, sent out the surveys all over the world, it just happened that people from white Caucasian ethnicity responded to it more than from any other ethnicity. And unfortunately, it happens. So as you can see, it doesn't always need to be intentional. And regardless of intention, bias undermines the internal validity, our confidence that the observed effect is real, and also external validity, which is our ability to generalize the findings to other settings. So for me as well, if my survey mainly had participants from the white Caucasian ethnicity, I cannot generalize the findings to other ethnicities such as Black African American or Asian or Pacific Islander. So I need to be careful when I make any conclusions, for example, in the manuscript or in the paper I'm writing. And as readers and researchers, our task is to be bias detectives, so to identify where bias might have crept in and how much it affects the conclusions that we are making, either as a researcher or even just a reader when you're reading a already published paper. And there are many types of bias, but let's walk through the most common ones. First, we have selection bias, which occurs when participants are not representative of the target population. For example, imagine a study on exercise habits that only includes gym members. The findings wouldn't generalize to the entire population because those individuals are already more active because they're going to the gym regularly. Then we have measurement bias, which is also sometimes called information bias, and it arises when tools or procedures distort what is being measured. A poorly calibrated device, for example, inconsistent questionnaire administration, or subjective assessment can all lead to measurement bias. Then we have performance bias, often occurring in intervention studies when participants or researchers behave differently based on knowledge of the group assignment. And this is why in randomized controlled trials, we use blinding to try to minimize this. Detection bias happens when outcome assessors are influenced by expectations. For instance, if an evaluator knows who received treatment, they might unconsciously rate symptoms as better. So this is, again, why we would have blinding. And further attrition bias occurring when participants drop out at unequal rates, changing group characteristics mid-study. I have seen this happen with published studies for Parkinson's when I was doing a systematic review, and this is what lowered my quality for my systematic review because there was a, let's say, somewhat equal participant sample from similar age groups, and then very generalizable from all ethnicities, and then let's say most people from one ethnicity all dropped the study, and then we only have people from other ethnicities left. So we have to see also that at that stage. So it's not only you who's running, for example, the trial, but also if you're doing the systematic review, it will essentially then lower your quality there as well. And finally, we have reporting bias, one of the most pervasive ones, actually. And it appears only certain results are reported, typically those that are statistically significant or favorable. And this skews the published record and overestimates any effects. Again, I think I spoke about this as well when we had the class on systematic reviews. So unfortunately, a lot in my Parkinson's research, I saw that a lot of trials are published with favorable results, and other trials that have been registered, like you see there's a clinical trial registry, their results have never been published, even if the trials are already old and like ended 5 years ago. And that made me question, like, why is that happening? So it's probably because some results are not favorable for the treatment, so they're avoiding to publish that. And this is reporting bias. So they will publish only the results that they like to publish because it looks good for them and their product. And understanding these biases equips us to critically read research and to design our own studies more rigorously. When we are appraising quantitative studies, then we focus on methodological rigor, how carefully the study was designed and executed. First, as I mentioned, randomization ensures that participants are assigned to groups in a way that minimizes bias. but randomization alone isn't enough. We also need allocation concealment and ideally the blinding. So neither the participants nor the researchers know who is in which group. In case of a drug trial, that would be that nobody has an idea if the patient is receiving the drug or the placebo. Secondly, sample size and statistical power are key. A study with too few participants might miss real effects, and that's a type 2 error, or exaggerate findings due to random variation. Third, controlling for confounding variables is also crucial. Confounders are external factors that influence both the independent and dependent variables. For example, in a study examining coffee and heart disease, smoking could be a confounder. So anything from the outside, so another external factor that will influence your results. So if we're going to look, for example, if coffee would be causing heart disease, then those participants who are smokers, that will be the confounding variable because it might be the smoking actually causing the heart disease instead of the coffee. Or maybe it would be smoking together with coffee, meaning that they somehow have an interaction which then leads to heart disease. So these are things that we don't know. We cannot tell from our experiment, and that's why that external factor is a confounder. Fourth, check whether measurement instruments are validated. Where psychological scales tested for reliability in, for example, a psychological study. If you are in the lab, then were lab assays standardized? And using unvalidated measures undermines credibility. So if you remember our lectures from survey research, it is also very important that we use validated instruments also for surveys. So these are these validated scales and that has been used in that certain population. Because then we can show that somebody else did it and it's credible and it's working, and then we are using it for our research as well. And finally, statistical reporting must be transparent, showing effect sizes, confidence intervals, and limitations. If the analysis is unclear or incomplete, then interpretation becomes risky. And together, these criteria tell us whether a quantitative study's findings are solid or fragile. And now if we shift our attention to qualitative research, such as interviews, focus groups, ethnographic work, or thematic analyses, they require a different lens for quality appraisal. Unlike quantitative studies, which rely on numerical data and statistical validity, qualitative research values depth, context, and meaning. And that doesn't make it less rigorous in terms of research, but it means that we judge quality by different criteria. The first concept is credibility, which parallels internal validity. So credibility asks, are the findings believable and well supported by data? Did the researchers spend enough time engaging with participants and analyzing their responses to truly understand their perspectives? And here you can also think about why it might be harder to analyze quality in qualitative research, because what the participant answered in an interview can be interpreted differently by different researchers who are listening to that response. So I might interpret it differently than any of you, and you all will have different like interpretations between each other as well. So this is why we might have a group of more researchers, and we need to really see how we can make sure that we understood. And this is why it's really important to come back to what questions we're asking in the interview, so that we're asking them as specific as possible, so that the response that we get has as less interpretations as possible. So we can't interpret it in 1,000 different ways. Further is transparency. So high quality qualitative work clearly documents how data were collected and analyzed, how themes were developed, how transcripts were coded, and how the researchers ensured consistency in interpretation. Again, very similar to quantitative research with the transparency that you're just documenting every step of the way what you did. And here in this case, it's also important to, as you see, note, so how did you ensure the consistency in interpretation? Again, taking us back to how we're asking the questions clearly enough, specifically enough, and then how are we interpreting it? So do we have any criteria for the interpretation? And a third criterion here is reflexivity. the researcher's awareness of how their own background, assumptions, and biases might shape data collection or interpretation. This is especially important in studies involving sensitive topics or close researcher participant interaction. So with the reflexivity, this is something that any person will have. So we will have our own opinions, we'll have our own biases, and this is where we try to minimize it when we're doing qualitative research. Because as I said, the participant might answer something in an interview question that you ask them, and you might have a completely personally different opinion from that. And that might introduce a way how you start interpreting that person's answer. So you might introduce bias because of that. And again, best here to do is, especially if you have a larger group of researchers, maybe even take people from like different areas. Like it doesn't have to be what exactly you are studying, but just as long as you can, same way as in an ethics committee, minimize this bias, especially for the interpretation part, just by taking people from just different backgrounds who have different opinions on a certain topic instead of just having this one strong opinion. Further triangulation refers to using multiple data sources, researchers, or analytical approaches to verify findings. If a theme appears consistently across interviews, observations, and documents, then that convergence increases credibility. Again, yeah, the triangulation, I already mentioned that for having the researchers, the more you have, the better, especially for qualitative research. And also, of course, using multiple data sources. So you're trying to just introduce more, more team members, more data sources so that you can increase the credibility of your findings. And finally, we have rich description and transferability. Good qualitative research provides enough contextual detail that readers can judge whether the findings are transferable to other settings or populations. And this doesn't mean generalizability in the statistical sense, but rather contextual resonance. So when reading qualitative studies, you should always ask if the story is authentic, transparent, and well supported by the data. And if so, then it is quite high quality evidence in its own right. From personal experience, I have mostly appraised and evaluated quantitative studies because that's how what my research mostly involves. I have tried to done it with a qualitative study, and I can only say that it's much more complicated also for me. And I think there's still much more to learn about appraising a qualitative study, and it just takes more time and let's say more thought than just appraising maybe a quantitative study, which is more focused on the numerical data. To make quality evaluation systematic rather than subjective, we use structured appraisal tools, and there's quite a few of them. One widely used framework is called CASP, which is the Critical Appraisal Skills Program. You might have heard of it already. And CASP offers checklists for various study types. So you have randomized trials, cohort studies, qualitative research, and systematic reviews, and you can download them from the CASP website. Each checklist poses simple but powerful questions, such as, for example, was the study design appropriate to the question? Are the results valid? Are they applicable to your context? And so on, so on. CASP is especially useful for teaching and journal clubs because it encourages thoughtful reflection rather than mechanical scoring. Further, we have the Joanna Briggs Institute, JBI, suite of tools. And JBI provides detailed design-specific critical appraisal checklists, one for each type of study, from quasi-experimental research to case reports and economic evaluations. And JBI also emphasizes transparency in decision-making and the documentation of how each criterion was judged. So I haven't used the JBI, it hasn't been applicable to my research, but I have used the CASP tool. And finally, the grade. So that's the one that I use the most. When we need to go beyond single studies and assess the overall strength of body of evidence, so for example, in a systematic review, then we would use grade. And grade stands for grading of recommendations, assessment, development, and evaluation. And it is the most widely used framework in evidence-based medicine and public health. Each of these tools brings structure and consistency to the evaluation process, ensuring the judgments about quality aren't based on intuition, but on explicit criteria. So let's take a closer look at grade, since it underpins many systematic reviews and clinical guidelines, and may be applicable if any of you are planning to do a systematic review. Grade begins by classifying evidence based on study design. Randomized controlled trials start at high quality. Observational studies would start at low. Then the evidence can be downgraded or occasionally upgraded depending on specific factors. 5 main domains can lower confidence in the evidence. So for example, first would be study limitations, meaning any risk of bias or methodological flaws in the included studies. That would lower your confidence and therefore get downgraded for the evidence. Secondly, you have inconsistency, when different studies show conflicting results or unexplained heterogeneity. For example, if you saw that you have very significant heterogeneity in your meta-analysis, then you would rate it as inconsistency, which would then again downgrade your certainty of evidence. Third, we have indirectness, when the evidence doesn't exactly match the research question. So for example, studying a related population or a different dosage. In this way, it's not as direct as it should have been. And here again, you would downgrade your certainty of evidence. Then we have imprecision, meaning wide confidence intervals or small sample sizes that make the estimate uncertain. And lastly, publication bias, where negative or null studies are missing from the literature. And again, if you joined my class 2 weeks ago on systematic reviews, we talked about funnel plots. So if you do a meta-analysis and you generate a funnel plot and you have like, it looks like that, so like a triangle, and you have a line in the middle, and if you see the studies, like most of them are symmetrical, meaning there's same number of studies on each side of the triangle, then you don't have publication bias. But if you see a clear gap, that there's like studies missing on one side, then most likely there are actually missing studies, and therefore you have the publication bias, and then you would downgrade in this part of the evidence as well. When several of these factors are present, then we may move from high to moderate or even low or very low confidence in the results. Importantly, grade makes this process transparent. Readers can see why reviewers rated evidence as they did, and that transparency enhances credibility. And again, as you see, the grade itself is a validated framework, and this is why it's important to use something like that, not just make any conclusions on why we would have low certainty of evidence. So we actually have it documented and written that we have these problems in these studies, and this is why our evidence is low. For me, with my Parkinson's research, I often saw very low evidence because we had publication bias. We also had inconsistency and imprecision, which would downgrade the evidence to low or even very low. And I reported that accordingly in my systematic review. So the peer reviewers and the editors of the journal can see that and see that I used a validated framework for it. And next time you read a systematic review and see a statement such as the certainty of evidence was low due to inconsistency and precision, then you will understand exactly what the researcher did and what that means. So if you would read a systematic review that I have published, then you would see me use such sentences there as well. And if we put this into practice, you can imagine now a randomized controlled trial evaluating a new drug for Parkinson's disease, picking again Parkinson's disease because that's my research. The study is randomized and blinded, which gives it strong features, but the sample size is very small and the follow-up of the treatment lasts only 6 weeks. So we would likely rate its quality as moderate because internally valid, but limited in precision and the long-term applicability. And practicing this reasoning helps you read literature with a critical and evidence-based lens. You also must remember that every study has limitations, even the best of studies. The question is not whether limitations exist, but whether they meaningfully affect confidence in the results. If you start with sample size and representativeness, small samples can produce unstable estimates and reduce generalizability. If the sample is biased, for example, only one gender or one socioeconomic group, then we can't assume that the findings apply to a broader population. Next, we should consider the control group. Is it appropriate and comparable to the experimental group? A control that differs systematically can introduce confounding. And this is why always, well, most of the time, the control group should be at least in the demographics, and everything should be equal or very similar to the experimental group. Duration and follow-up, of course, also matter. So a short clinical trial may show initial benefit that fades over time, while loss to follow-up can distort long-term outcomes. And look at how outcomes are defined. Vague or subjective outcomes reduce clarity. For example, if we say improvement in symptoms without specifying any measurement criteria. Finally, must check for unclear reporting or missing data. When methods or results are incompletely described, it is difficult to evaluate validity. Missing data, especially if not random, can bias results. A good paper openly acknowledges all these issues, and ironically, the presence of a well-written limitations section often signals higher quality because it demonstrates transparency and critical reflection. Again, important for both your systematic reviews and your, for example, survey research, your original research, is to always think about all the limitations for your research and write about them openly, because other researchers and also peer reviewers in journals, they will read that and they will make sure that you don't think that your research is perfect, because no research is perfect, and that you are able to acknowledge these limitations and maybe, improve them in your next study. So that is the most important part, that you are able to acknowledge that you have limitations. And one of the defining features of modern science is its growing emphasis on reproducibility and transparency. Again, those two terms that we already talked about today. But for decades, the scientific community assumed that published results were inherently trustworthy. But the replication crisis in psychology, medicine, and other fields has shown that many findings can't be reproduced, sometimes because of statistical errors, and sometimes because of selective reporting. Transparency means making research methods and data openly available so that others can verify and replicate the analysis. It involves sharing any protocols, data dictionaries, code, and analysis script whenever possible. So you might see a published study and it will say that either it has supplementary material already available, or you can request it from the authors. So if you are interested in, replicating and seeing if the results will turn out the same for you, you can email the authors, or you can just check the supplementary information. Maybe it's already openly available. And also, if it's not, then the author should provide it to you, and you have the right to try to replicate the study and see if you come up with similar results. And then we can see if we had any selective reporting or anything else. So this is why these nowadays, all these published studies, they usually have a lot of, let's say, that would maybe previously be confidential information, such as like protocols and code, but now it will be publicly available information, just to make sure that our research is actually, valid. Pre-registration of protocols. So for clinical trials, you would use clinicaltrials.gov or any open science framework. Also helps prevent selective reporting and p-hacking, which means running multiple analyses until something significant appears. So this is why a lot of times these protocols are also registered. I see a lot of them for clinical trials. This is why I said that I've seen that there are registered trials which have already finished years ago, but there's no publication for their results. So this is why I thought that there's something missing, or that they, chose not to publish the results. And this is why such databases actually help you identify that, or at least raise suspicions for you as a researcher. And replication studies are also vital. So they might not be glamorous, but they are the foundation of scientific reliability. When independent teams replicate findings using different data and still reach the same conclusions, then our confidence in that evidence will skyrocket, because as I said, then we are completely independent teams, but we come basically to the same conclusion, and we can then start, saying that this research has high quality, and we can be sure that the way that our findings are, those are the true findings, and not just picked out or biased. Encouragingly, more journals now support open data and register reports, also, as I mentioned in the supplementary information. And this shift doesn't only protect us against misconduct, but it also enhances the collective credibility of science. Another major threat to the overall quality of evidence is publication bias. Also, we touched on it already shortly today and a lot 2 weeks ago. Publication bias occurs when studies with positive or statistically significant results are more likely to be published than those with null or negative findings. And this means the published literature provides a distorted picture of reality. What I have noticed doing research is that it's not just the researchers who don't want to publish these, let's say, negative findings or null result. Unfortunately, a lot of times researchers do want to publish them, but when they go to a journal, they get rejected because the journal thinks it's a waste of their time or space to publish it, unfortunately, even though that shouldn't be that way. And unfortunately, a journal is also more likely to accept a manuscript for publication if the results are positive and statistically significant. So we can not only blame the researchers, we can also blame the journals that just don't want to publish findings that they don't find so interesting. And generally, this problem is often called the file drawer problem because all those non-significant studies end up sitting in file drawers and they're unseen. And the consequences here can be serious. Meta-analyses that rely on published data can overestimate treatment effects, giving a false sense of certainty. So if we've published the trials on a Parkinson's drug that only show that it's improving the motor symptoms for Parkinson's, and then let's say left in the drawer all the trials that said that the same drug does not significantly improve the motor symptoms, then the meta-analysis that we conduct on the published results will obviously show that the treatment has great effect on motor symptoms in Parkinson's patients, when in reality that might not be true. So this is why it can be a serious problem in research. And yeah, there can also be an example of analyses of antidepressant trials, which have shown that when unpublished data are included, then the apparent effectiveness drops substantially. And this is why at some point we had a lot of saying that antidepressants are really helping. But then when we have looked at the unpublished data, when that came out, from the dark, then we realized that, actually the effectiveness will drop substantially. Researchers use several strategies to detect or mitigate publication bias. As I mentioned about the triangle, so the funnel plot can visually reveal the asymmetry when small negative studies are missing. And trial registries like clinicaltrials.gov can be checked to see whether completed studies remain unpublished. So this is also another thing I did with my Parkinson's research. And some journals now explicitly accept null result papers to reduce this bias. So we see that there are journals now doing that, but unfortunately, a lot of them, like I said, especially the high impact factor journals, remain very leaned towards these positive and significant findings just because they think that then they will have more readers and how we all want something more interesting rather than maybe having null results. So recognizing publication bias reminds us that absence of evidence is not evidence of absence, and that the full picture of research often lies beyond what is actually published. Once we have identified strengths, weaknesses, and biases, the final task is synthesizing our quality judgment. Appraisal isn't about finding one fatal flaw. It's about weighing multiple dimensions. So design rigor, bias control, sample adequacy, and transparency. A study might be methodologically sound, but poorly reported, or innovative, but underpowered. Our job is to integrate these aspects into a balanced assessment. It is also vital to remember that quality does not equal importance. A small qualitative study can offer profound insight, even if it doesn't score high on formal appraisal tools. Conversely, a massive trial can be low quality if poorly conducted. And finally, good researchers are transparent about their own judgments. When you write a review or critique, state explicitly how you rated the evidence and why. And that transparency allows others to understand your reasoning and potentially disagree, which is healthy for scientific dialogue. So let's summarize the process of evaluating research quality step by step. Step one, you identify the study design and question, and you ask yourself, what kind of study is this, and what is it trying to answer? Knowing whether it's experimental, observational, or qualitative determines which criteria will apply. Step two, you assess internal and external validity. So, are the results credible within the study? And are they generalizable to other populations? Step three, you examine bias and confounding. Think about who was included, how outcomes were measured, and whether important variables were controlled. Step four, evaluate transparency and reproducibility. Did the authors report their methods fully? And could someone replicate this work with the information that is provided in the methods? Step five, you make an overall judgment using frameworks like GRADE. You can summarize your confidence in the results and rate them as high, moderate, low, or very low. And this structured process transforms reading from a passive act into an analytical skill. And you're not just accepting results that you read, but you are interrogating the evidence that is behind them. So to close, let's distill today's lecture into a few essential take-home points. So first, quality defines credibility. Without methodological soundness, even the most exciting results lose meaning. Second, bias and validity are at the heart of every critical appraisal, whether it is a clinical trial, a survey, or a qualitative interview. Ask where bias might have entered and how it affects validity. Third, structured tools such as CASP, JBI, and GRADE help bring consistency to your judgments and allow you to communicate them transparently. Fourth, transparency and reproducibility are the new gold standards. Sharing data and methods strengthens the collective reliability of science. And finally, remember that all research has limitations, but good research acknowledges them honestly. Our goal is not just to find perfection, but to interpret findings with a balanced and critical mindset. And by applying these principles, you will become not only a better researcher, but also a more discerning reader and contributor to evidence-based practice. So thank you for your attention. I will now take any of your questions. So we have 15 minutes for that. Also, if you have any questions outside the class, you can email me to the email on this slide.